Hey, welcome. Today, we're going to break down one of those concepts you use every single day without even realizing it, volume. And we're going to uncover a secret master key that unlocks how it works for almost any shape you can think of.
Okay, so let's start with this. Picture it. You're packing. You've got these 3 bags in front of you. A boxy hard case, a duffel bag with those kind of triangular ends, and a round, tube-like container. They all look totally different, right? Your gut might tell you one's bigger, but how do you really know for sure? Well, this isn't just a packing puzzle. It's a math problem, and it's all about volume.
So what is volume, really? At its core, it's just the amount of three-dimensional space an object takes up. A good way to think about it is like this. How many tiny little 1-centimeter sugar cubes could you fit inside something? That number, that's its volume in cubic centimeters. Now, it is super important not to get volume mixed up with surface area. They're related, sure, but they are totally different things. Volume is the stuffing, how much stuff fits inside the box. Surface area is the wrapper, how much cardboard you need to make the box. Today, we're all about the stuffing.
All right, so let's ease into this. We're going to start with the shape we all learned about in school, the good old-fashioned box. Or, if you want to be fancy, a rectangular prism.
The formula here is just beautiful. It's so simple. You literally just multiply its 3 dimensions, the length, the width, and the height. That's it. You're done.
So let's say we have a box that's 6 centimeters long, 4 centimeters wide, and 7 centimeters high. We just crunch the numbers. 6 times 4 is 24, and 24 times 7 is 168. Boom, the volume is 168 cubic centimeters. You could fit exactly 168 of those little cubes inside.
And here's a really key idea this shows us. What happens if you turn that box on its side? Does it suddenly hold less stuff? Of course not. The sides you call length, width, and height might get swapped around, but you're still just multiplying 6, 4, and 7. The volume stays exactly the same.
But here's the thing. That simple little box formula is actually hiding a much more powerful secret. A kind of master formula that can handle not just boxes, but tons of other shapes. Yeah, including the other 2 bags from our trip.
Okay, let's really look at this. The formula again is volume equals length times width times height. So just focus on that first part. What part of the box is just length times width? What is that calculation actually finding?
It's the area of the bottom of the box, right? The flat surface it's sitting on. So really, you're just taking the area of the bottom and then multiplying it by how tall the box is. And that, right there, is the master key. The volume for any prism or cylinder, basically any shape that has the same face on both ends, is just the area of that face, or base, multiplied by its height. You find the area of the repeating shape, and then you just multiply by how far back it stretches. That's the whole secret.
So the big question is, does this master key actually work? Let's go back to our other bags and put it to the test.
First up, the duffel bag. It's really a triangular prism. So the base is that triangle at the end. We find its area, half the triangle's own base, times its height, which gives us 24 square centimeters. Then we multiply by the length of the bag, which is 7. And what do we get? 168 cubic centimeters. That sounds familiar.
Okay, what about the cylinder? What's its base? It's a circle. So we find the area of that circle, pi times the radius squared, which is about 41.85 square centimeters. Now multiply that by its height of 4 centimeters, and we get about 167.4. Wait a minute, are you seeing what I'm seeing here?
So let's just lay it all out. The volume of our boxy hard case was 168 cubic centimeters.
The volume of our triangular duffel bag? Also exactly 168 cubic centimeters. And the cylinder, about 167.4. I mean, that's basically the same. So, the answer to our original question, which one holds the most, is that they're all pretty much identical. Even though they look completely different, they all hold the same amount of stuff. So, why should we care about this beyond a packing puzzle? Well, it has huge implications for pretty much everything we buy. Because volume is only half the story. The other half is that wrapper, the surface area. Just take a look at this. We've got 2 different boxes, but they have the exact same volume. They both hold 60 cubic centimeters of stuff. But now look at their surface areas. Box 1, the one that's shaped more like a cube, only needs 94 square centimeters of cardboard. Box 2, the flatter one, needs 104. It needs more material to hold the exact same amount of product. And that right there is $1 million idea. Seriously, If you're a company shipping millions of things, choosing a shape that holds the same volume but uses less surface area can save you an absolute fortune in material costs. It's all about finding the most efficient wrapper for the space you need.
So if you're going to remember just one single thing from this entire explainer, please let it be this next idea.
Don't just memorize formulas. Understand the logic. For any of these regular shapes, the volume is just the area of the base times the height. Find the area of that one repeating face, and then just see how far back it stretches. That simple, intuitive idea is the key to everything.
And that leaves us with one last thing to think about. If the most efficient way to hold space is to use the smallest possible wrapper, where else do you see that principle at work? I mean, think about things in nature, like a soap bubble or a honeycomb, or look at engineering and design. The answer you'll find is absolutely everywhere.